Welcome again. Today we will discuss organic reagents based on silver and rhodium. So, you can see rhodium and silver, they are in the same row, the fifth row, and rhodium is in the group of cobalt and silver is in the group of copper. So, we will see first the silver, organic reagents based on silver, and here we will discuss first Woodward cis dihydroxylation, then Prevost reaction, then silver mediated addition of nucleophiles to alkynes, oxygen nucleophiles, nitrogen nucleophiles, then silver 1 mediated addition of nucleophiles to allenes, oxygen nucleophiles, nitrogen nucleophiles, also silver mediated addition of nucleophiles to alkenes, oxygen nucleophiles, nitrogen nucleophiles, and silver 1 mediated cycloaddition reaction. So, first we will see Woodward cis hydroxylation. This is an important reaction developed by Nobel laureate Woodward. So, the dihydroxylation is effected in 3 stages. Iodine and silver acetate first interact to form an intermediate which converts the olefin to an iodoacetate by trans addition. This occurs when the reactants are shaken in dry acetic acid solution at room temperature. So, first you have to shake with dry acetic acid in iodine and silver acetate. The second stage, replacement of halogen, is effected by silver acetate in acetic acid containing the required amount of water. This is also important, the water you have to present by heating for 3 hours at 100 degree centigrade or for 1 hour at the reflux temperature. And the mono and diacetates are finally isolated and hydrolyzed. So, this is the mechanism, this is the alkene, and the iodinium ion is formed first, iodinium ion, like bromine reaction, iodine also reacts similar way, and here this iodinium ion is formed. Now, silver acetate reacts with this iodinium ion, as you can see it is reacting here. So, here the groups are inverted, and now you get this intermediate that is open through nucleophilic substitution by acetate anion. So, this is nucleophilic substitution, and now iodine will be coordinated with silver plus. So, that we will see. So, in the second stage, a neighboring group participation, this is important. A neighboring group participation mechanism prevents the intermediate nucleophilic substitution of iodine by a second equivalent of acetate. Instead, a cyclic acetoxonium ion intermediate is formed that will lead to a syn substituted product. So, this is very important. Whenever a neighboring group is present, then the neighboring group can react with the electrophile. So, the substitution reaction happens with the neighboring group, because it is a intramolecular process and that is quite fast. So, here the acetate anion is present in such a way that it can do a nucleophilic substitution, and with elimination of silver iodide you get this cyclic oxonium ion. So, this is the cyclic oxonium ion, and this can be in resonating structure with this carbonium ion. There is a positive charge here, carbonium ion. In contrast to the course of the Prevost reaction that we will see, in Prevost reaction you cannot use water, but here you have to use water. Water appears to add readily as a nucleophile to the partially positive carbon atom of the intermediate. The cyclic orthoacetate is then cleaved to a monoacylated diol. So, this is the carbonium ion, and now water attacks to generate this. So, you see the stereochemistry, this is actually syn. So, we will see that when this water attacks to the carbonium ion, you generate this and then it is opening actually. So, either the acetate will form this carbon atom or this carbon atom, whatever. So, this is actually monoacylated diol. You get a mixture of monoacylated diol, but after hydrolysis you get the diol. So, after hydrolysis you get diol, single product. So, this is the reaction happening with iodine silver acetate acetic acid and followed by acetic acid water reflux. That cyclooxynium ion is reacting with water and then the monoacylated diol is formed. And so, like this monoacylated diol is formed, that after hydrolysis will give the diol. So, now we will see the Prevost reaction. So, in the Woodward reaction it is the syn addition, but Prevost reaction we will see this is trans addition, and the Prevost reaction allows the synthesis of antidiols from alkenes by the addition of iodine followed by nucleophilic displacement with benzoate in the absence of water. So, this is very important. In the absence of water, hydrolysis of the intermediate diester gives the desired diol. So, this is the overall reaction with silver benzoate. So, this is silver benzoate and iodine in benzene, you get this. So, this you can see, this is the trans. So, trans dibenzoate, and after KOH H2O treatment you get the trans diol. So, what could be the mechanism here? Similar to the Woodward reaction, the initial addition of iodine leads to cyclic iodinium ion, which is opened through nucleophilic substitution by benzoate anion. So, this step is similar like Woodward reaction. So, similar to Woodward reaction, like alkene reacting with iodine generating the iodinium ion, and earlier we have seen the silver acetate, here the silver benzoate is reacting. So, you get this opening of the iodinium ion by the silver benzoate and you get this species like this, and a neighboring group participation also happens here. Neighboring group partition mechanism prevents the intermediate nucleophilic substitution of iodine by a second equivalent of benzoate that will lead to a syn substitute product. Instead, a cyclic benzoxonium ion intermediate is formed. So, here also the neighboring group participation happens because the neighboring group is within the molecule. So, the reaction will be always faster when there is a neighboring group, and after silver iodide elimination you get this oxonium ion. So, similar like Woodward reaction, you get the oxonium ion and this will be equilibrium with the carbonium ion. So, up to this it is similar, and now here only the difference, because if you do not add water, then opening this intermediate by a second addition of benzoate gives the anti-substituted dibenzoate. So, instead of water, if you have excess benzoate, then this benzoate will open. So, benzoate will give an inversion here. So, ultimately you get the trans dibenzoate. So, you get trans dibenzoate. So, this is very important. Earlier when water added, then the stereochemistry did not change, but now benzoate is attacking here. So, there will be inversion in this center, nucleophilic substitution SN2, and hydrolysis then delivers the diol. So, what are the drawbacks of this reaction? The use of expensive silver salts, the requirement for a stoichiometric amount of molecular halogen, and the formation of a relatively large amount of organic and inorganic wastes. That are the drawbacks, like silver iodide will form. Now, we will discuss organic reagent based on silver, some cyclization reaction. So, silver mediated addition of nucleophiles to alkynes, oxygen nucleophiles, and phenyl propyrzylidine malonic acid. So, in the gold catalysis we have seen that gold complexes with alkynes very well. Similarly, silver also complexes with alkyne very well, and defined addition reaction can be done. Like with phenyl propyrzylidine malonic acid. So, this is the phenyl propyrzylidine malonic acid when R is equal to pH. So, with this triple bond double bond is there, and with silver nitrate one equivalent. So, this was the first report actually in 1958 by Kastner and Pascual. So, they first developed this, that the alkyne can coordinate with silver. And after alkene coordination with silver, from silver nitrate, the carboxylic acid can do a reaction here. So, here you can see this is 5-exodic and this is formed by 6-endodic. And 5-exodic is measured when R is equal to pH. So, and when R is equal to alkyl, then you get mixture of 2 and 3. So, with silver nitrate 1 equivalent methanol 25 degree centigrade, just starting in methanol 20 at room temperature, you get these products 70 to 90% yield. And not only phenyl, other aromatic groups can also be tolerated. After this development, many other groups tried to exploit this chemistry and many different cyclizations have been reported. Like here, this is actually cyclohexadiene system, cyclohexadiene, and carboxylic acid there and alkyne is present with N-propyl group. Now, they develop the silver iodide or silver 10 mole % only, and when DMF solvent you get 74% yield of this 5-exodic. So, 5-exodic is the measure here. The 5 member ring is formed and this triple bond becomes double bond of course, and this is an important molecule, it is called lingastrelide. You get this product in 92:8 ratio. So, this product is from 8%, this is from 92%. This is formed 6-endodic. Now, if you treat this propargylic alcohol, so propargyl alcohol, and this is a quaternary center. So, first you have to generate a carbonate with CO2 dBu 1 equivalent, you generate this carbonate, this is carbonate, and after that you treat with silver acid at 10 mole %, and then the activation of the alkyne by silver will happen and the desired cyclization will happen. So, this is also, so 5-exodic, then you get these cyclic carbonates. In 76 quantitative yield. So, this method is very useful to generate cyclic carbonate with an exocyclic double bond, and you can see R1, R2 can be methyl, ethyl, phenyl, etc. R3 can be hydrogen with terminal alkyne also, then internal alkynes PH, PH, CH2, CH2, CH3, OCH2, etc. group can be incorporated. So, this method is quite general that alkyne can be activated with silver and then different oxygen nucleophile can react and get different cyclic product. So, this is in Chemical Reviews 2008 3174 is the page number, there you can get this different heterocyclic synthesis by silver. So, now we will discuss the mechanism for silver catalyzed cyclization of. So, this is alkynoic acid, here a triple bond, double bond, and this is acid. So, with silver, as always silver will coordinate with the triple bond, and now there is, this is the exo, this is endo possible with Z is equal to hydrogen or silver. So, when 5-exodic will happen, 5-exodic, then you get this, after addition silver will be always in the trans. So, this is very important, trans orientation, incoming nucleophile and silver will be in the trans orientation of the double bond, and after silver X elimination, and this is actually H plus is coming. So, silver plus is displaced by H plus either from solvent or work up with water, you get this. So, this is the 5 membered cyclic products. This is butidolactone with a double bond, actually 2 double bonds are present, one internal another external, and with 6-endodic you get this. So, here you can see this attack happens here and you get silver here, and again silver X elimination and H plus, of course, you get this 6 membered ring. So, this is very important that always the silver will coordinate with the alkyne and then 5 exo dig or 6 endo dig will operate depending on the substitution. So, the formation of the 6 member lactone via endotype lactonization is not favored. At this point, factors affecting the pyranonone-furanonone ratio are not yet very clear, although it is known that the ratio between the two products is strongly dependent on the substrate structures, the nature of silver salt and the solvent. So, depending on the substrate structure and silver salts and the solvents, you can get different ratio of these two products. This was also reviewed in the chemical reviews 2008, page number 3174. So, now we will see nitrogen nucleophiles. So, not only oxygen, nitrogen nucleophiles can also be used, and here also you can get different aza products. So, pyrrole annihilation has also been achieved by silver promoted oxidative cyclization of homopopargylic amines, like this one, a homopopargylic amine. Here with silver acetate 1.1 equivalent DCM, you get this pyrrole. So, this is important, this is aromatic. So, not only the addition, there also dehydrogenation is happening, that we will see. So, this nitrogen is attacking, and then after aromatization you get this product pyrrole. So, what could be the mechanism? So, here also silver coordinates with the triple bond, and here the 5 endo dig will happen, 5 endo dig will happen, and you get this intermediate. So, the coordination of the alkyne to the silver cation initiates an equilibric attack of the amine to the alkyne, leading to an intermediate. Protonation affords the iminium ion. So, this is iminium ion, and this is very important. Now, this iminium ion will undergo beta hydride elimination, that will generate pyrrolium ion and metallic silver. So, you can see after beta hydride elimination, so what will happen? This silver hydride will eliminate, and that is ultimately will go to silver plus 0.5 hydrogen. So, after beta hydride elimination, you get this pyrrolium ion. So, this is pyrrolium ion, and now H plus will eliminate for the aromatization. So, like this H plus eliminate and generate the pyrrole. So, this is very important. When you put homopopargylic amine with silver acetate, you can get the pyrrole, substituted pyrrole actually. This is 2,5 disubstituted pyrrole you can get very easily. This was published in Organic Biomolecular Chemistry 2004. More examples of nitrogen nucleophiles. Here you can see the tetrahydroisoquinoline derivative, like this group is there, the triple bond has a trimethyl group. Here also with silver acetate 1.1 equivalent you get this pyrrole formation. So, here also similar mechanism, and beta hydride elimination and then the proton loss will give this aromatic product, and this can be hydrogenated to make this compound which is called crispin A, and this is an anti-tumor agent. So, this is very important, you can get easily this pyrrolidine fused tetrahydroisoquinoline by this strategy. Also, if you have a imine here and a triple bond here, then with H nucleophile is this nitromethane, nitroethane, malonitrile, and with silver sulfate only 3 mole %, then you can get this intermediate, because this nitrogen will first attack here, then this will happen. So, this is 6 endo dig. 6 endo dig will happen, and now this is iminium ion, here the nucleophile will attack, and you can get this product in 56 to 85% yield. So, R1, R2 can be phenyl, N-butyl allyl, and nucleophile I already told nitromethane, nitroethane, and malonitrile can be used. So, this is very important, you can get this compound alkaloids very efficiently with the incoming nucleophile is present here. Also, N-bridge pyrrole can be formed by this strategy, propargylation of secondary enaminones using N-butyl lithium and propargyl bromide and an intramolecular hydroamination catalyzed by silver nitrate. So, with butyl lithium and propargyl bromide, you can get first this. So, here butyl lithium will take, and now this will attack here and this will happen, and after the isomerization of course you get this, because iminium ion will form, that will isomerize to this is much more stable. And now after silver nitrate, so what will happen, silver nitrate, so after silver nitrate addition, so nitrogen will add here and you get this after proton loss, and this will isomerize to give this. So, after isomerization you get this is the aromatic part, this part. So, silver nitrate microwave condition you can get 71 to 75% yield. So, this is two-step process, first N-butyl lithium then react with this enaminone. So, this is enaminone with propargyl bromide you get this. Now, you put silver nitrate catalytic amount and microwave condition, this is 5 exodig is happening, and after isomerization you get the aromatization. This was published in Tetradan Letters 2004, page number is 6787. So far we have seen the alkyne, now we will discuss allenes. So, allenes can also be used in this hybridization strategy. So, first we will see oxygen nucleophiles and allenones to furans. So, this is allenones, you can see this is a carbonyl group present with the allene, and with silver nitrate or silver tetrafluoroborate acetone or acetonitrile solvents you can get these products, these are furan and multi-substituted furan actually, multi-substituted furan. You get these products in 70 to 99% yield. Here R1 can be hydrogen, this is the R1, hydrogen means aldehyde, CH3 means ketone, CO2 CH3, CH2OSC, CH2O-mom, R2, R3 can be hydrogen, CH3 isobutyl, tarbutyl. So, different groups are possible, this is a very general method and you can get this furan. So, what will be the mechanism? So, here in the allene generally the terminal double bond reacts. So, terminal double bond reacts because of steric region. So, in the allene there are two double bonds and now silver will coordinate to the terminal one, and now this is only possible here. So, 5 endo trig is happening, and so the process is initiated by coordination of silver ion with the allynic pile system. Attack by the carbonyl oxygen will lead to the oxocation. So, this is the oxocation, and here this reaction is happening and silver goes here, and after elimination of proton loss from cation will result in the silver 1 furan intermediate. So, after proton loss, so this proton will be lost and you get this silver containing furan. So, this is silver 1 furan, and now of course, H plus will come and silver plus will eliminate, you get the furan. This could undergo direct protonolysis with loss of silver 1 to afford furan product. Deuterium incorporation experiment supports this mechanism. So, if you put deutero, then here you can get deuterium. So, this is very important method to generate furan from allenones. If you put the allenones with silver nitrate or silver tetrafluorate with acetonitrile solvent, you can get very good product. This was published in JOC 1990. Now, we will see stereospecific synthesis of dihydrofurans. This allene and also this is secondary alcohol, this is chiral, these are stereocenters. And you see with silver nitrate 0.8 equivalent, calcium carbonate 0.8 equivalent in acetone water solvent, you get this. This is dihydrofuran, fused, of course, fused dihydrofuran, you get 60% yield, and the stereochemistry are retained. This is very important. Stereochemistry retained. Also, you see this is chiral allene, this is chiral alcohol, there is another chiral center with silver nitrate 0.2 equivalent, acetone you get this. So, all these cases 5 endo trig cyclization is happening. Here also the stereocenters are retained. Here you see this group is there in the starting material also. This was published in Journal of Organic Chemistry 1993. Now, if you have this one you can see the lactam is present, also tertiary alcohol with a quaternary center, this is the allene, and now this we will add here and you get this dihydrofuran, and the stereochemistry is intact. So, also in this condition this is acetonide. So, acetonide, because the reaction happened with acetone water, you get the hydrolysis. So, this goes to diol, and here the cyclization happens selectively, and this motif is undisturbed in this reaction. So, different groups can be tolerated, R1, R2 can be methyl phenyl benzyl PMP group. This work was published in Advanced Synthesis Catalysis 2007. Now, we will discuss synthetic routes to butenolides. So, you see here the allene is group and carboxylic acid. So, allene carboxylic acid. So, here what will happen, this if you get the A star can be converted to the acid by treatment with boron trichloride, then you can get the acid, and that acid if you treat with 10 mole % silver nitrate in acetone solvent, you can get this butenolide. So, this is butenolide. So, this butenolide compounds you can get very easily by reacting allene carboxylic acid with silver nitrate 10 %, and you can see R1 can be NC5H11, this is the allyl group, then the cyclohexyl group, and this is of course racemic. So, this is racemic, and now a chiral synthesis is possible, chiral allene carboxylic acid. So, if you prepare chiral allene carboxylic acid like this way, this is the propargylic alcohol, you have to put a methyl protection, and this product you can get in 95% E, and then this one PDPPH3 whole 4 and carbon monoxide, you get this. So, here the allene is formed, this methyl group eliminates. So, carbon monoxide ultimately will go to CO2H group, here it is attacking like this, and you get the allene and as well as the carboxylic acid group. Now, this substrate is very much suitable for our reaction, that is the 5 endo trig cyclization. So, 5 member ring will form like this. So, silver will coordinate here and this hydroxy will attack here, you get this. So, here the stereochemistry also is retained the methyl group, and you get this product after treating with 10 mole % silver nitrate, you get this product in 62% yield and 90% E. So, you start with the product with 95% E and you get 90% E. So, enhancer selectivity is almost retained. So, this is very important. During this cyclization, the enhancer selectivity did not lose so much. So, enantiomer selectivity is almost retained. Starting metal was 95% and the product you get 90% enantiomeric excess. And this is very important product, this is marine furanosembran rovifolite. And this work was published in Journal of Organic Chemistry 1997, page number is 367. So, now we will discuss nitrogen nucleophiles. So, wherever oxygen nucleophiles will work, nitrogen nucleophiles also work. So, nitrogen nucleophiles to allenes we will see, and synthesis of delta 3 pyrrolines. Like here, this is also you can see this is chiral allene system as well as extra chiral center is present here. This is the amino ester motif, and with silver nitrate 0.2 equivalent acetone solvent you get this product in 83 to 95% yield. So, these are delta 3 pyrrolines, and R1 can be methyl benzyl isobutyl, R2, R3, R4 can be hydrogen benzyl methyl TMS isopropyl N-butyl, different groups can be screened, and this work was published in Organic Letters 2001. So, here also this similar reaction is happening, 5-endotrig. So, 5-endotrig is happening, the silver coordinates with this terminal double bond, and then this attack happens, and here this stereochemistry is retained like oxygen nucleophiles also. This stereochemistry is also retained, and you get this cis geometry here, CO2Me and R3 will be cis. So, now we will discuss allynic sulfonamide cyclization. So, this is sulfonamide and this is allene, and here also you can get the same 5-endotrig cyclization and this N-tosyl groups as here. So, here silver coordinates and here the attack happens, and after proton comes, of course, the silver will eliminate and you get this center. So, here when Ar is equal to 4-methoxy pH, then you can get cis is measured, cis is to trans is 64 is to 36, and this is the condition, silver nitrate 0.2 equivalent, this will be potassium carbonate 2 equivalent, and acetonityl solvent you get this product. So, here this base is required, this is the acidic proton NH tosyl. So, after deprotonation only this becomes active nucleophile. And now, this you can see this is carbamate motif, carbamate, and this one there is a carbamate motif, there is a allene motif, and with AgNCO 10 mole percent, triethylamine, here also you have to use a base like triethylamine 10 mole percent benzene, you get this cyclic product. So, this is cyclic carbamate is forming, and you see here because this ring is only possible 6 exo, because 6 or 5 member ring you will form in GI. So, here 6 exo trig cyclization is happening. So, silver is coordinating here and this nitrogen attacking here, and you get this double bond vinyl group. When R is equal to hydrogen, these are hydrogen, R1 is equal to methyl, then trans is ratio is equal to 11:1. So, this is the trans one. So, this will be, and when methyl both is methyl, R is equal to methyl, R1 also methyl, then 7:1. So, trans is major, and this was published in Bulletin of Chemical Society Japan 1995, page number is 1689. Now, we will discuss silver mediated addition to alkenes. So, alkenes can also be used in this reaction, intramolecular addition of alcohols and carboxylic acid to inert olefins catalyzed by silver 1 triplet. Like here there is a double bond and alcohol with 5 mole percent silver triplet, DC 83 degree centigrade, you get this tetrahydrofuran and tetrahydropyran. So, tetrahydrofuran and tetrahydropyran. With carboxylic acid also you get cyclization, you get the lactone 5 membered or 6 membered, and we will see depending on R1, R2 you get this ratio. The silver ion binds and activates the double bond, which is then attacked by the oxygen nucleophile on the opposite phase. This apports an intermediate with the newly formed carbon oxygen bond position trans to the silver carbon bond. subsequent proton transfer results in the formation of the product and regeneration of the silver 1 catalyst. So, this is the mechanism. So, silver coordinates with the double bond. So, like it coordinates with triple bond alene, it can coordinate with the double bond also, and then there is R of course. Then the 5 exo addition will take place. So, this will attack here and then you get this, and after H plus comes you get this one and silver plus will regenerate. So, when R is equal to H, then this is major, when R is equal to methyl, then this is minor. So, this is very important. Now, 6 endo will give this product. So, 6 endo case here it will attack R. So, when R is equal to methyl, then this will be major, because the attack will take place the more substituted carbon, and there the carbonium ion of course will be stable. So, R is equal to H, this is minor, R is equal to methyl, this is major, and this is the paper Organic Letters 2005. So, this is very important. When there is a disubstituted olefin, that is the olefin, the terminal carbon it is disubstituted, then the 6 member ring tetrahydropyran will form. On the other hand, if it is monosubstituted olefin, then you get the tetrahydrofuran. So, silver catalyzed sequential CC and CO bond formation between phenols and dienes also is possible here. This is phenol, this is diene. So, here this attack will take place, followed by silver mediated cyclization will give this, and different groups can be tolerated here, and with 4 methoxy group, R is equal to 4 methoxy, here the methoxy group, then silver triplet gives 60% yield, silver chlorate 40%, silver tetrafluoroborate 30%, and AgSbF6 only 20% yield. This was published in JOC. So, here the silver is acting as a Lewis acid, Friedel cup reaction is happening, followed by the oxocyclization. Tetrahydrofurans and tetrahydropyran through silver assisted phenyl selenoetherification also is possible. Here you see PHSCX with silver oxide, silver acetate catalytic or 1 equivalent, X is equal to chlorine bromine, phenyl selenium chloride or phenyl selenium bromide. You get this cyclization, that is ether formation like this, and of course, a selenium ion is formed here, and without silver also this reaction occurs and you get 75 to 80% yield. Now, catalytic amount of silver will increase the yield to 85-90, and 1 equivalent silver 1 give 95 to 100% yield. This work was published in this journal in 2003. Now, again we will discuss pyrrolidine synthesis. So, this is a Ajakov rearrangement. So, Ajakov rearrangement will happen. This reaction developed by Stott. So, he is famous organic chemist. So, if you have this one CH2CN group with NME group, and this is the allylic alcohol, then with silver nitrate treatment you get this. So, the ring expansion happens and pyrrolidine is formed, and they are also syn orientation, and different groups can be tolerated, you get 75 to 95% yield. So, what could be the mechanism? So, first silver cyanide elimination. So, this iminium ion will form. So, this is the iminium ion, and then the 3,3 Ajakov rearrangement will happen. So, this will add here, now this will go here, and this will go here. So, here this enol is formed. After that the Manning cyclization will happen. So, this will be like this. So, this is here it is connecting R and this. So, you get the Manning cyclization, 7 member ring is formed, and this reaction is happened very diastro-selectively. So, diastro-selectively, because of the ring requirement, this is syn. Always when there is a sp2 center, it likes to take and syn orientation. This was published in JACS 1988. Now, silver mediated cycloaddition reactions are also possible. 1,3 dipolar cycloaddition reactions of azomethane ylides. Here there is a hydrogen and that remove with a base, and then you can get the azomethane ylide. And now different Electrophile can be treated like here methyl acrylate will give this. So, this is the endo product CO2Me and AR are in the same side. Also maleimide can give this product, bicyclic product, this is also endo, and with dimethyl fumarate also silver acetate base will give this pyrrolidine. This is tetrasubstitute pyrrolidine, very important, and this is the major product. Here also CO2Me AR on the same side. So, this is the endo and this is exo isomer. And activation of amino esters behave like 1,3 dipole. If you put base, then this dipole will form, and this dipole will interact with the silver, and this syn dipole will form, and this syn dipole then react with this defined dipolorophile and to give this cycloaddition. This is also reviewed in the chemical review 2008. So, silver catalyze as a Diels-Alder reaction is possible. Here silver behave as Lewis acid like here imine, and this is Denisevsky's diene, with silver 10 mole percent THA minus 78 degree centigrade binap or toluene binap, you get this product in 75 to 90% yield, and different groups are tolerated. R1 CO2 phenyl, R2 is equal to tosyl benzyl phenyl CO2 etc. So, this is racemic version, and this is chiral version. So, same reaction Denisevsky's diene and the imine, you get this. So, what happens like this way reaction happens, this will react here and this nitrogen will react here, and after methanol elimination you get this double bond again. With silver acetate 0.1 to 1 mole percent isopropanol solvent, you get 78 to 90% yield, and the enantiomeric excess is 88 to 95% with this chiral phosphine. So, chiral phosphine and imine is present. So, they of course will bind with the silver, and silver of course coordinates with the imine nitrogen. So, the chiral environment is formed, and that is why you get the enantiomeric excess, and AR can be phenyl, naphthyl, furyl etc. This work was published in Anguk Chemie 1998. So far we have seen the silver mediated synthesis. Now we will see rhodium based reagents in organic synthesis. So, first we will discuss Monsanto process, then Tennessee Eastman acetic anhydride process, then we will discuss cycloaddition reaction, and then we will discuss hydrosilylation reaction. So, organorhodium chemistry is the chemistry of organometallic compounds containing a rhodium carbon chemical bond, and the study of rhodium and rhodium compounds as catalyst in organic reactions. Stable organorhodium compounds and transient organorhodium intermediates are used as catalysts such as olefin hydroformylation, olefin hydrogenation, olefin isomerization, and the Monsanto process. Rhodium can exist in oxidation state of +1 to +5, but rhodium 1 and rhodium 3 are the more common. Rhodium 1 compounds D8 configuration usually occur with square planar or trigonal bipyramidal geometry, while rhodium 3 compounds D6 configuration typically have an octahedral geometry. So, first we will discuss Monsanto process. The Monsanto process is an industrial method for the manufacture of acetic acid by catalytic carbonylation of methanol. So, this is the process for the manufacture of acetic acid from methanol. The Monsanto process has largely been supplanted by the Ketiva process, a similar iridium based process developed by BP Chemicals Limited, which is more economical and environmentally friendly. This process operates at pressure of 30 to 60 atmosphere and temperature of 150 to 200 degree centigrade and gives a selectivity greater than 99%. It was developed in 1960 by the German chemical company BASF and improved by the Monsanto company in 1966, which introduced a new catalyst system. So, this is the carbonylation reaction. So, carbonylation of alcohol, this is the Monsanto process. Methanol plus carbon monoxide, you get the acetic acid. Also, olefins and alkynes can be carbonylated, like here olefins shows H2, you get the acid, and with alkene carbon monoxide H2 you get the aldehyde. So, when additionally H2 is given, then the aldehyde, and H2O is given, then you get the acid. So, we will discuss this reaction. Monsanto process, catalytic cycle, the catalytically active species is the anion cis RHCO2I2 minus. The first organometallic step is the oxidative addition of methyl iodide, that we will see. Methyl iodide, this is formed from methanol plus HI. So, that we will see how HI is coming. Addition of methyl iodide to cis RHCO2I2 minus to form the hexacoordinate species CH3RHCO2I3 minus, and the anion rapidly transformed by the migration of methyl group to an adjacent carbonyl group affording the pentacoordinate acetyl complex. Like always happens, the methyl group inserts into the metal carbon monoxide bond. Thus, this 5 coordinate complex then reacts with carbon monoxide to form the 6 coordinate dicarbonate complex, which undergoes reductive elimination to release acetyl iodide, and this acetyl iodide only will generate the HI. So, the catalytic cycle involves 2 non-organometallic steps: conversion of methanol to methyl iodide, hydrolysis of the acetyl iodide to acetic acid and hydrogen iodide. So, this is the catalytic cycle, this is the active catalyst here, active catalyst RHCO whole to I2 minus. Here this methyl iodide will react. So, methyl iodide will form from methanol, HI will react to give water and methyl iodide. This methyl iodide will add here. So, this is CH3 group and this is I. So, now this is hexa coordinate. Now, the insertion will happen. So, this is the migratory insertion will happen. This CH3 group inserts in this metal CO bond and get this CO CH3 group. Now, again another carbon monoxide will come. So, again it will be hexa coordinate. So, this will be again hexa coordinate after additional carbon monoxide, and now reductive elimination. Will give this acetyl iodide, one iodide, and this acetyl group will generate acetyl iodide, and this catalyst is regenerated. Now, this acetyl iodide reacts with water. So, this is very important, this reaction happens in presence of water. So, the acetyl iodide gets hydrolyzed with water to generate acetic acid. So, this is the product and HI. So, this HI will generate methyl iodide after reaction with methanol. So, methane is the starting material and this is the product. So, you see this is reviewed in by Hartwig in organotransition metal chemistry from bonding to catalysis, University Science book, New York 2010. So, there are some benefits of Monsanto process. Uses a more efficient metal complex to synthesize a carbon-carbon bond, increase yield selectivity greater than 99% based upon methanol, milder conditions needed for the synthesis 150 to 200 degrees centigrade and 30 to 60 bar, plant capacity 5 lakh tons annually, challenges rhodium expensive and precipitates under low water concentrations, large production of high boiling point byproducts like AHI will form, replaced by an iridium catalyst in the late 1990s by BP Chemicals. So, now we will discuss Tennessee Eastman acetic anhydride process. So, this process, as you see, this is generating acetic anhydride. So, this process should be done in the anhydrous condition. So, acetic anhydride is produced by carbonylation of methyl acetate in a process that is similar to the Monsanto acetic acid synthesis. Methyl acetate is used in place of methanol as a source of methyl iodide. So, this is the reaction. So, this is methyl acetate, carbon monoxide will generate the acetic anhydride. In this process, lithium iodide converts methyl acetate to lithium acetate and methyl iodide, which in turn affords through carbonylation acetyl iodide. So, here also acetyl iodide is formed. Acetyl iodide reacts with acetate salts or acetic acid to give the anhydride. This is important. Rhodium iodides and lithium salts are employed as catalysts because acetic anhydride hydrolyzes. The conversion is conducted under anhydrous condition in contrast to the Monsanto acetic acid synthesis. The main difference between the Monsanto acetic acid process and the Tennessee Eastman acetic anhydride process is the presence of water in the acetic acid process, which produces HI and acetic acid. In both reactions, a small amount of H2 is added to the CO system to act as a reducing agent to keep the catalyst in the more active rhodium oxidation state. So, one difference is the Monsanto process, you have to use the water that will generate the hydrolysis of acetyl iodide to acetic acid, and in this case you cannot use the water. Here the acetate anion will react with the acetyl iodide to generate the acetic anhydride. So, this was the reviewed in catalysis today 1992, and this is the catalytic cycle. If you see clearly, then this cycle is same, this is same like Monsanto. Here this is the active intermediate, methyl iodide is coming, this is happening, then the migratory insertion carbon monoxide is happening, and this is also same with acetyl iodide. So, this is same. Now, here the methyl acetate will generate methyl iodide by reacting with lithium iodide, and in this way it is generate this acetic acid lithium salt, and that is reacting with the acetyl iodide to generate acetic anhydride. So, this is the product and this is the starting material. So, earlier in the Monsanto this was getting hydrolyzed to acetic acid, here it is reacting with this anion of the acetic acid to generate this. So, that lithium iodide is forming, that lithium iodide is reacting with the methyl acetate to generate methyl iodide. So, this is the Tennessee Eastman acetic anhydride process. Now, we will discuss cycloaddition reaction. Chiral rhodium phosphine complexes can be employed as efficient catalysts for cycloaddition reactions. For example, rhodium 1 complexes having diene and chiral biphosphines catalyze intramolecular 4+2 cycloadditions with excellent stereoselectivity. Like here, this you can see, this is nicely suited for 4+2, there is a triple bond, there is a diene, and with 5 mole % rhodium Cl L star. So, L star is this chiral diene and diphosphine. This is the diphosphine like DuPhos, this is also chiral, and 20 mole % AgSbF6 dichloromethane room temperature. You get this product 26% E, 91% yield without phosphine, and when PPH3 is added, then also same E, 26%, 85% yield. So, this tells that not only diene, you have to use a chiral diphosphine. That is why when RR ET DuPhos is used, this enantiomeric excess increase to 95% E, and you get product also high yield, 99% yield. So, both are important. COE is cyclooctene. So, diene is not present. So, phosphine is important here with 6 mole % L star, that is R is equal to pH. So, R is equal to pH. So, this is almost 2 phosphine group are present, and this product is formed. This is also 4+2, and this bicyclic compound is formed in 87% E, 76% yield. So, with phosphine ligand here is NR to give the enantiomeric excess. Here also this same catalyst. So, 2.5 mole % rhodium cyclooctene whole 2 Cl whole 2, 6 mole % L star R is equal to pH, that cases you get the cyclization product 4+2, and when R is equal to methyl, then you get 73% E, 84% yield. On the other hand, R is equal to pH, that case you get 47% E, 73% yield. So, what does it mean? So, R is equal to methyl case, R is equal to methyl, then the catalyst is C2 symmetric. So, then C2 symmetric catalyst is giving good E for this kind of cyclization when there is a methyl group. This is the terminal double bond is methyl group, here the internal carbon has the methyl group. So, this was published in Tetrahedron 1994. So, what is the mechanism? So, here this phosphine will coordinate, also this diene will coordinate with rhodium. So, this is the active catalyst. Now, this triple bond and one double bond will coordinate with rhodium to generate this species, and now oxidative cyclization will happen. So, after oxidative cyclization, this bond will form carbon rhodium here, here also carbon rhodium. So, 5-member ring is formed, first 5-membered ring with rhodium like this, and another double bond is there of course, and now the ring expansion will happen. Here what happens? Now, this carbon rhodium bond breaks and it attacks here, and you get this, a double bond is here, and this is the methyl group. So, it attacks here, so generate the methyl group hydrogen selectively, and now the reductive elimination will happen. So, then reductive elimination, you get this, and rhodium gets eliminated, and this chiral center you get there, methyl is down. So, chiral center is retained there, and this is of course trans geometry, hydrogen and methyl are in the trans. This was published in JACS 2006. Now, last reaction we will discuss hydrosilylation. Hydrosilylation of alkenes is not only of industrial importance, but also one of the most popular means that afford functionalized organosilicon compounds of synthetic applications. The rhodium 1 catalyzed hydrosilylation of alkenes with anti-Markovnikov selectivity. So, this is formal anti-Markovnikov like borane addition. An effective route for the synthesis of O1 silyl alkanes, the adducts can be subjected to an efficient oxidative cleavage of the silicon carbon bond, transforming into 1 alkyl non. So, this is diene rhodium catalyst HSiMe2PH, dimethyl phenyl silane, then this SiMe2PH group goes to terminal, and this double bond rearranges here, and after oxidation you get this. So, OH is at the terminal carbon. So, that is the formal anti-Markovnikov addition. Asymmetric version of this reaction can be accomplished with high enantiomer selectivity. For example, rhodium binap complexes catalyze asymmetric intramolecular hydrosilylation of alkenes with high enantiomer selectivity. Like here, if you use this C2 symmetric phosphine, C2 symmetric bisphosphine and rhodium, then this formed intermediate. So, here these two are seen. So, this is the newly generated chiral center, and silyl takes the terminal carbon, and after oxidation you get this diol. Syn anti greater than 99:1, 98.3% yield, and R is equal to 35Me2C6H5CH3. This R group, silyl R is equal to 35Me2CH3. So, today's reaction, first we have seen silver mediated cyclization reaction. So, we have seen the addition to alkynes by oxygen as well as nitrogen nucleophiles, and different cyclic products are formed. Then we have seen the addition to allenes. So, allene case we have seen in general the allene coordinates with silver at the terminal double bond, and then you can get the endocyclization product. Also, you can get exocyclization like when OCONH tosyl group is present, carbamide motif, that case we have seen the 6-exo dig is forming. Then we have seen the double bond. Double bond also can be coordinated with silver, and you can generate formation of tetrahydrofuran, tetrahydropyran. Also, pyrrolidine formation we have seen, pyrrolines formation with the addition of nitrogen nucleophiles to double bond. And Before that, we have seen the Woodward cis hydroxylation. In the cis hydroxylation, you have to use the water acetic acid, and the previous method, that trans diol is formed, that case you cannot use water. So, that case the benzoate will externally do the substitution on the intermediate cyclic oxonium ion, and that is why you get the trans product. And also you have seen the silver can catalyze many cycloaddition reaction. 3+2, this is we have seen azomethane ylide and defined dipluorophile, and also 4+2 cycloaddition also we have seen, that is the azadyl reaction with denisapsyldiene we have seen. And with rhodium catalysis we have seen the Monsanto process. This is the acetic acid preparation from methanol and carbon monoxide with rhodium catalyst. We have seen the active intermediate is acetyl iodide, which is hydrolyzed to acetic acid, and this HI forming, HI is converting methanol to methyl iodide, and that methyl iodide is adding to the rhodium system. On the other hand, 10SA system you generate the acetic anhydride from methyl acetate carbon monoxide. Here also acetyl iodide is formed, but you cannot use water. Here what happens, the acetate, the lithium acetate, that is adding to the acetyl iodide, and you get this acetic anhydride and lithium iodide. That lithium iodide is converting methyl acetate to methyl iodide. And then we have seen rhodium catalyzed cycloaddition reaction. We have seen if there is a triple bond and double bond also with chiral diene and chiral phosphine, you can generate the product in asymmetric way. Thank you.